Welcome back to another Explainer. Today, we're diving right into Chapter 4 of our physics journey, unlocking what I really love to call the invisible dance between moving charges and magnetism. We're going to be breaking down this chapter and showing you exactly how these fundamental invisible principles actually power pretty much our entire modern world. Let's get right into it.
We have to start with a profound historical mystery. I want you to picture this. It's the summer of 1820. A physics professor is giving a routine lecture demonstration, and suddenly, there's a simple, completely unexpected twitching of a nearby compass needle. That one little twitch completely revolutionized human technology. But how? How did a tiny, seemingly insignificant movement rewrite the fundamental laws of physics?
Well, here's our roadmap for figuring that out today. We'll kick things off with that 1820 discovery, then move into the Lorentz force, calculating the field, solenoids and loops, and finally wrap up with a real-world application, the galvanometer.
Okay, part 1. The 1820 discovery, unifying two forces. It's wild to think about, but for over 2 millennia, electricity and magnetism were seen as completely, fundamentally separate things. A lightning strike was one phenomenon, and naturally magnetic lodestones were just something else entirely. No connection whatsoever. For literally 2,000 years, there was absolute separation. But then, that massive conceptual wall just came crashing down with Oersted's discovery in 1820. And look at the acceleration on this timeline. That single observation directly paved the way for James Clerk Maxwell to unify both forces mathematically just a few decades later in 1864. Talk about a paradigm shift. The pioneer who kicked this all off was a Danish physicist named Hans Christian Ørsted. As the story goes, he was running a lecture, passing a pretty large electrical current through a straight wire, and he noticed, almost by accident, that it caused a noticeable deflection in a nearby magnetic compass needle. When he looked closer, he realized the alignment of that needle formed an imaginary circle with the straight wire right dead center.
So, the absolutely crucial takeaway Ørsted had was this. A static electrical charge, one just sitting there doing nothing, does absolutely zero to a magnet. But the very second that charge moves, the moment a current actually flows, this invisible dance begins. The moving charge literally generates a magnetic field in the surrounding space. Movement is the key to the whole thing.
Which brings us to part 2, the Lorentz force, the rules of the dance. So, now that we know moving charges create magnetic fields, let's kind of flip the script. Let's look at how existing magnetic fields exert forces on moving charges. What are the actual ground rules for this interaction?
Well, the Lorentz force mathematically defines exactly what happens here. If you look at the equation, we can see the total force depends on the particle's charge, its velocity, and the magnetic field, plus any electric field that might be hanging around. The magnetic portion of this force is entirely dictated by that cross product right there, between velocity and the magnetic field.
And honestly, this brilliantly illustrates some highly counterintuitive physics. Unlike gravity, which just pulls straight down, or electric forces that pull straight toward a charge, the magnetic force acts completely sideways. It's perfectly perpendicular to both the velocity and the field. Plus, if the charge stops moving entirely, poof, the magnetic force simply vanishes. And strangely enough, even if a charge is moving incredibly fast, if it happens to travel perfectly parallel to the magnetic field, the force is still zero. Mind-blowing, right?
Let's move on to part 3, calculating the field, Biot-Savart and Ampere. Because understanding the force a field exerts is really only half the battle. To really master this chapter, we need to know how to calculate the actual shape and the strength of the magnetic fields created by these currents.
When we compare electric and magnetic fields, specifically using the Biot-Savart law, a fundamental difference emerges. Static electric fields come from a simple scalar source, literally just a point charge, sitting there. But magnetic fields, they require a vector source. They're produced by a current element, which means both the magnitude of the current and its specific direction are absolutely essential to mapping out the resulting field.
Now, calculating those fields piece by piece using Biot-Savart can be a mathematically grueling process. But just as Gauss's law gives us a shortcut in electrostatics, Ampere's Circuitola law offers this incredibly powerful mathematical shortcut for magnetism. By drawing a closed, symmetrical loop, Ampere's law directly relates the magnetic field along that boundary to the total steady current trapped inside it. It's a remarkably elegant tool when you're dealing with symmetric situations.
All right, part 4, solenoids and loops, scaling up the dance. Let's zoom out from the microscopic math for a second and look at macro, physical applications. Like, what actually happens when we take these field-generating wires and intentionally coil them up?
Well, that brings us to the solenoid, an absolute staple of modern engineering. A solenoid harnesses those exact laws we were just talking about. By winding a wire into a tightly spaced helix, you're essentially summing up all the tiny individual magnetic fields from multiple circular turns. The result? You get this highly concentrated, incredibly uniform magnetic field shooting straight down the center of the cylinder. And even if we just zoom in on a single circular current loop, it's fascinating. It turns out a simple loop of current acts exactly like a tiny bar magnet. It's a magnetic dipole with its very own north and south poles. This realization was actually so profound at the time that it led Ampere to suggest that all natural magnetism, like in those ancient lodestones, is really just the result of hidden microscopic circulating currents within the atomic structure itself. Finally, Part 5, the galvanometer, physics in action. So, why does all this invisible dancing matter to our daily lives? Let's look at a foundational piece of tech that utilizes absolutely everything we've covered today, the moving coil galvanometer.
The galvanometer is basically the physics of this entire chapter brought to mechanical life. Think about it. When you run a current through the device's coil, an external permanent magnet pushes it sideways thanks to the Lorentz force. And because it's a coil, that sideways push translates into rotational torque. The coil literally twists. But it doesn't just spin out of control. There's a tiny attached spring that balances that twist by providing a counter-torque. The exact point where those two forces equalize gives us a precise physical measurement of an invisible current.
And the brilliant part is how adaptable this thing is. This one simple application of magnetic torque is insanely versatile. By just tweaking the resistance, say adding a small shunt in parallel to measure massive currents, or throwing a large resistance in series to measure voltage, this single device becomes the foundational tool for analyzing practically any electrical circuit. As we wrap up our explanation of Chapter 4 today, I want to leave you with a bit of a mind bender, drawn straight from the end of the text. We established early on that magnetic force only happens when a charge is moving, right? Well, what if you were instantly placed into a reference frame running right alongside that moving charge, traveling at the exact same speed? To you, the charge is entirely static. Therefore, in your reference frame, the magnetic force completely vanishes. The actual physics changes depending on how fast you're moving. So it begs the question, is magnetism really just an illusion, a weird side effect of relativity in movement? Think about that, and keep exploring the amazing connections in our physical world. Catch you next time.